Okay, everyone, thanks for coming to our October webinar. Today we've got Tom Sherman here. We're going to talk about motors and VFDs. I'll tell you briefly how I know of him. Tom is he's an AEE member. He's been presenting at the AEE World for quite a long time. How long have you been going to these events, Tom?
About 15 years.
15 years. Okay, so he's been going for about 15 years, presenting for several of them. And I was looking through talks that people have given, and this one looked really interesting to me. So I reached out to Tom, and he said he'd do it. And so here we are. Hey, Tom, why don't you tell them who you are and jump right into it?
Sure. My name is Tom Sherman. I'm founder and president of Sustainable Energy Services, and we're all about energy, just like John. I speak at the World Conference, the East and West Conference, many years, as well as other conferences. And one of the topics that I get most often to present is about motors and VFDs, and that's what we're going to do today. So motors consume 28% of the US electric output, so it's a pretty big deal. If we can find ways to save energy on motors, it would have a big impact on, not only decarbonization, but also reducing emissions and save a lot of money. And that's what we're going to talk about. 28%, that would be greater than 1 trillion kilowatt hours a year. Imagine saving, 50% of that with VFDs. That would be something. So there's many types of motors, and we're not going to go through in detail this slide. I just want to give you kind of a sense of how many choices you have on motors, both AC, DC, and electronically controlled motors. So there's, for every application out there, there is a motor that's available. I would say the motor that's missing from this chart is the one that Tesla uses on their cars. It's actually a dual motor, but we're not going to get into that in the details because we're going to try and keep this fairly basic. And so let's start off with the basics here. I always like to describe rotational space and time using an old slinky. If we close up the slinky and turn it one way, we see a perfect circle. If we turn it the other way and expand it, we see a perfect sine wave. And this is the way motors like to operate because power is delivered as a sine wave and it actually rotates it perfectly. When that sine wave isn't perfect, the rotation isn't perfect. It's held, the motor's of course held tight by the bearings, but it is not operating efficiently and it's generating heat because it's not a sine wave. So a sine wave is ideal. When we look at the Faraday lens law, the Faraday law is the third in Maxwell's equations, if you remember that from your E&M course in physics. And the way it works, and we'll explain it three ways. Here we'll do it with a flow chart. So a changing magnetic field is reinforced by an iron core that's in the motor. It induces its own EMF or voltage, and that voltage drives an alternating current, which induces its own changing magnetic field, which is opposing the original magnetic field. And that's where the force comes from for rotational movement on the motor. One of the ways I like to demonstrate this in classes is I take a copper pipe and a rare earth magnet. When I drop that magnet through the pipe, if it's a steel ball, it drops in less than half a second, hits the floor with a loud bang. Everyone knows it dropped like, the way it would with gravity. But then I switch it to a rare earth magnet, and the magnet will fall down. But because it's a magnet and it's inducing a current in the copper pipe, there's an opposing magnetic field. And so this magnet now moves very slowly through the copper pipe. And whether the magnet is, weighs an infinite amount of weight or it's a feather, it's still going to move, because if it doesn't move, there's no opposing force. So there has to be some movement for that opposing force to be present. And this is how motors operate. If you take that copper pipe, that becomes the stator, and the magnet becomes the rotor. And you just change the physical configuration, and then the motor will rotate. So this is the third presentation of the Faraday lens law. For those of you that enjoy math, I thought I would do the differential equation so that you can see mathematically how this works. I won't spend time on it since I've already explained this equation with the flow chart. A few motor facts: standard efficiency motors. These are motors that are installed before 1997. Typical efficiency is 83 to 90%. The Energy Policy Act of 1992 tried to improve energy efficiency on motors because of the large load, as we saw earlier. Typical efficiency is 87 to 92%. Then in 2007, with the Energy Independence and Security Act, it was, the hurdle was raised again to NEMA premium motors, which are typically 91 to 95% efficient, depending on their size. The larger the motor, the more efficient. The Department of Energy extended the range for premium efficiency motors with effectivity in June 2016. What they decided was that trying to go from 95 to 98% was a fool's errand. It's just not going to work to try and up the efficiency even more. What they did instead was include a broader class of motors in the category for premium efficiency. And you can see the new rule adds the NEMA class A, B, C, the IEC N and H class, and we're going up to 500 horsepower now, where it was only 200 horsepower before. So the evolution of motor efficiency here, you see in the chart. The red chart is the standard efficiency curve. EPAC went to 200 horsepower, and you can see that in the yellow. And now with the new DOE extension to 500 horsepower, you see the green and the efficiency of motors today. Three-phase motor construction. We talked about that copper tube and the ball bearing. Well, they take the place here. We have a stator and we have a rotor core. This is what creates that rotating magnetic field. As you see the poles in the stator, what happens is that the magnetic field is rotated around that stator, and that's what rotates the rotor. Here you can see an example of a 10 horsepower motor designed with the different efficiencies. What makes a motor more efficient is the additional material. These are the same 10 horsepower, but you notice that when you move to standard through EPAC through premium, how the stator gets much bigger and the rotor gets much bigger. You have much more material. So not only are you reducing the electrical resistance, you're also reducing the magnetic equivalent of electrical resistance, which is magnetic reluctance. Inverter grade motors, when you are using a VFD or an inverter, it's best to use a NEMA premium efficiency motor with the beginning and ending windings that are separated. Up until the inverter grade motors were developed, the windings always start and ended together. And with the voltage spikes present with VFDs, you have to protect against that, and you always want those beginning and ending of windings to be separated. Extra insulation is also added to protect against voltage spikes, and inverter grade wire is used, which is a heavier insulation, and it is designed to higher frequency components, which create losses. So heating is a big issue, and as you can see, the full rated torque at zero speed is very important. So you do get better torque at low speeds with a VFD. Here you see the major classes of motors, the induction motor, the synchronous motor, the permanent magnet motor, which are very expensive, and the motors that are reluctance motors, which are very specialized motors, using an inverter to run the motor, which is part of the design drive for the motor. And you can see that in terms of the rotor and stator, the speed, the efficiency, the reliability, power density, I won't get into all these details. You can kind of read it for yourself, but kind of let your eyes gravitate towards you know, the kind of motors you're using, and you can see the comparison between those motors and other similar motors. Motor efficiency versus load. Motors are designed to be optimal for efficiency at around 80%. That's where most are loaded. When you get below 40%, the efficiency really drops off. And motor slip is very important. So this is just an illustration of motor slip. Basically, the motor, in this case, the rotor, is always trying to chase the rotating magnetic field in the stator, and it can never get there. It can never catch up. If the car was to actually catch up to the magnet, you would lose all of your rotational energy. You want to create this this drag, if you will, so that the slip is always present, and this is what keeps it rotating. Determining motor load. First, we look at the speed, which is the 60 hertz times the 60 seconds per minute divided by the number of poles. That's your RPM. RPM is very naturally, in terms of the synchronized RPM, going to be 3,600 or 1,800 or 1,200. It's because of the number of poles. There's no other choices but just those numbers. The no load RPM is pretty much equal to the synchronous RPM, and the full load RPM comes off the nameplate of the motor. The measured RPM needs to come from the current curve for the motor, or what we normally do is we put a tachometer on the shaft and get a direct measurement off the shaft of what the measured RPM is. So the design slip is going to be the no load RPM minus the full load RPM. The true slip is the no load RPM minus the measured RPM. The percent load is true slip divided by design slip. So the true slip is going to be percent load times the nameplate. So if we do a quick example here, we have a full load RPM of 3555. So right there, you know that the synchronous RPM is 3,600. There's no other choice. The horsepower is 75. We go through the simple math, and you can see that we are 53.3% loaded, which means that 75 horsepower is running at 40 horsepower. Slip is not naturally created in single phase motors. So what happens is we add a capacitor, a starting capacitor, as you see right here. On single phase motors, you always see this little camel back here, and that's to create this circuit which causes a sine wave that's out of sync with the normal power sine wave, and that creates the starting torque. In terms of RPM versus torque, here you see torque on the y-axis and RPM on the x, and you can see what the natural curve is to this red dotted line. In actuality, what happens is there's a breakdown torque, and then there's a pull-up torque, and then a locked rotor torque. So this is a classic torque curve. Different classes of motors have different torque curves, and we'll get into that very briefly here. Here you see the NEMA design characteristics for different torque curves. They're design A, B, C, and D, and it depends on the application, which is the appropriate design for torque. So how you figure out torque, the horsepower is going to be the torque times the RPM divided by 5250. 5250 comes from 33 foot-pounds for a horsepower divided by 2 pi. So the torque is equal to the horsepower times 5250 divided by the RPM. Power factor, it's a big deal with motors. Lightly, loaded motors generate a very poor power factor. I see over on the right here, I put this Bierstein. I think this is a ubiquitous presentation of power factor that I think is wrong. And I wish they would stop using it, because what they like to say is that this foam is wasted power. But this wasted foam, as they call it, is the reactive power. Without reactive power, you don't magnetize the steel in the motor, you don't magnetize the steel in transformers, and guess what? We're back in the Stone Age because we have no electricity. Reactive power is key to magnetizing steel in our motors and our transformers. It's not wasted, it's purposed very intentionally to create the magnetic field that is needed for transformers and motors to work. But I did want to show you that this kVAR value here, it is necessary for the motor, but if you're lightly loaded, you can address this kVAR issue with two solutions. One is to use offsetting power factor correction capacitors, or use a VFD. A VFD will give you unity power factor at all loads. In terms of a quick check on power factor, you could look at a bill for a customer. You see in this case, the kW is 1500 and the kVAR is 1096.7. On your calculator, we know the angle here is going to be the kVAR divided by the kW. Take the arctangent of that quotient and take the cosine. The arctangent of this value is theta, this angle up here, and the cosine of theta is your power factor. Power factor, as you see, once you get below 60%, really drops off. And I've been in factories where power factor was 28% or 22%, and it's because invariably they have a lot of large motors that are lightly loaded. They didn't realize that when they changed their processes to not need as much horsepower, they should have changed the motor as well. What it costs to run a motor. Here you see the values that I selected here. It's important to understand there's a demand component in most tariffs. And here we have a 70% loaded motor. So the kilowatt hours is going to be the 100 horsepower times 0.746, which is your conversion from horsepower to kilowatt, times the operating hours, times the load factor, times the cost per kilowatt hour, and divided by efficiency. What we have to add to that, though, is the demand cost, which is going to be the same conversion to kilowatt times 0.7 for 70% load factor, times $11 for demand, times 12 months for the year. And when we add these two together, you see that we're over $44,000 to operate a motor that costs $6,000. So whenever you go to purchasing and they say, hey, listen, I found a real low cost motor for you, don't buy it. First look at how efficient it is in the application, and then decide if it's the right way to go, because you're going to pay a lot more for it every year than the purchase price. Is it worth switching to a NEMA premium? Absolutely. Using the same 100 horsepower motor in the previous slide, the annual operating cost is $44,000 compared to an older 87% efficient motor, which has a cost of $47,000. It's a difference of $3,500, closer to $36,000. So you're looking at essentially less than a 2-year payback if the motor costs $6,000. So VFD basics. The whole idea of VFDs is based on the affinity laws. So here you see a simple representation of the affinity laws You have your original horsepower, and then your new realized horsepower is equal to the ratio of the original RPM and the new RPM cubed. So if we solve for the realized horsepower, that's here, it's going to be equal to the original horsepower divided by this ratio cubed. So a 50% drop between the original horsepower and the new horsepower is going to be 88% less horsepower. If a 50% drop in RPM is going to create 87% less horsepower. So let's take a look at an example. Now I'm going to use real simple numbers here. Obviously, a motor doesn't operate at 3,600. It's going to be 3,565 or some number. But I'm just going to use the synchronous numbers at 36 and 1,800 to keep the example really, really simple. If we cut the horsepower by half, or the RPM by half. So we're using a VFD to reduce the the CFM or the RPM by half. Then here's the equation. We have 100 divided by, essentially it's 2 cubed, which is 12.5 horsepower. So you go from 100 horsepower to 12.5 horsepower by cutting the RPM in half. Very dramatic. So let's look at this example, and this is one that John and I were kind of talking about in prior weeks. You have a 50 horsepower motor running a fan at 1,800 RPM. You put on a VFD with 100 horsepower, and you now reduce the CFM by half because you're reducing the rotation of the motor by half because you put on a VFD at 50%. So instead of operating at 60 hertz, it's operating at 30 hertz at 100 horsepower. Sure, it's only 12.5 horsepower, but look at the difference in the delivered CFM. It's cut in half. So that's what's problematic about this particular arrangement. So is there an arrangement where this could make sense from an efficiency standpoint? Well, what if we started with 3,600 RPM on the motor? Now, when we cut it to 50%, it's the same RPM as the original 50 horsepower motor. We're still at 12.5 horsepower resulting in the end, but which is nice for the VFD. And we now matched the load, so they're both 1,800 RPM delivering the same CFM. Of course, in this scenario, you say, well, gee, it really does make sense to buy a larger horsepower motor and use a VFD. You save more money. Well, but your first cost, you've got that cost of the VFD and you got the cost of the larger motor. And you've got more points of failure. You've got maintenance, increased maintenance. So you got to factor all these into the equation before you just simply go and do this. But, you know, technically speaking, if I'm running this motor for the next 20, 30, or 40 years with this arrangement, I'm thinking I'm better off with the VFD on 100 horsepower to run that fan. The other thing with the affinity laws is, notice we kept the cube at 3. In reality, it's never 3. A rule of thumb is 2.7 to be conservative. With fans, I would use 2.7. It could also be lower than 2.7. And if you're filing for a rebate with a VFD on a motor, the utility is going to take a close look at this because it's not just the efficiency of the motor, but what is attached to that shaft. If you got a water pump and you got a gate valve on that water pump and that gate valve is used to modulate the volume of water, that's counteracting the benefit of the VFD on the motor, on the pump, and you're nowhere near 2.7. You're probably closer to 2.4, 2.3, or 2.1. So you got to be careful on the exponent here. Rule of thumb, use 2.7, but you have to look at what's attached to that shaft to really know where you need to be. Variable frequency drives are ideal for variable load, variable speed applications, unless you have a serious power factor issue that you're trying to solve and you can't change the motor. It's less ideal for constant load, constant speed applications. There is inherent soft start. I'm working with a customer now. It's got 7 400 horsepower motors, and they want a generator to run the motors for backup, and the generator company is misspecifying the load on the generator that it can take because they're ignoring the fact that VFDs are being used and they offer a soft start feature. Unity power factor at all loads, same variable speed and fast torque of DC motors. In fact, it's better than DC motors, but less expensive. The drive does add heat and stress to the motor, so that's why inverter grade motors are best. Drive makes the motor less efficient. Remember that whatever efficiency you have in the motor, when you got a VFD, you got about a 3 to 4% efficiency loss in that VFD. That adds to the overall efficiency of the system. So you can envision a VFD in 3 segments. You have your diode bridge. It could be an active bridge with SCRs. You have your DC choke and capacitor for your filter. And then you have your IGBT bridge, that's insulated gate bipolar transistor inverter bridge. Here you see a 6 pulse. You also have 12, 18, 24 pulse inverters. They even go higher than that. As you get higher and higher in power levels, you want more and more pulses, and I'll show you why here in a bit. This is the bridge that we're going to get into more details on. So in the bridge, a PWM, or pulse width modulated waveform, is used to synthesize a sinusoidal output. Now you can see these series of pulses, while they may, roughly construct a sine wave, it's a terrible sine wave in terms of, the fast DVDT that you see on these pulses. Here you see the difference between the waveforms on a 6, 12, and 18 pulse. A 6 pulse only for the smallest motors because of the inefficiency of the heat that's generated. As you move up in power, you really need to kind of clean up that sine wave and go with an 18 or even a 24 pulse to get the smoother waveform. And VFDs come in all sizes. Here you see both small, medium voltage and high voltage systems. So the VFD and the motor together. First, to diagnose these issues, you need to have the right tools, and you have like about $100,000 worth of tools right here. This is the stuff we use when we do motor forensics. And here's why we need these tools. We're looking at things like rapid DVDT. Here, if we look at a sine wave over on the right, the synthesis of a sine wave over on the right, you see that you have these on-off transitions on the IGBTs that create 5 megahertz ringing waves. These 5 megahertz ringing waves can be propagated down a DVD cable, the cable between the VFD and the motor. And when they propagate, they can resonate. And when they resonate, if they resonate, they can create very high voltage that's at least 3 times the DC bus. On a typical 40 volt motor, that's 1800 volts. Here's another way that the DVD pulses look at the terminal of the motor. You can see, in this case, a 40 volt motor, and we've got spikes, in this case, reaching up to 1600 or 1500 volts. This is where you get that punch through. The other issue you get is called corona inception voltage. So as you increase these voltage spikes on a motor, you have, due to a reflective wave on the cable, you can get these spikes that go above the corona inception voltage. And what happens is the insulation starts to ionize and creates carbon tracking for shorts. And this is a classic case of a VFD wound inverter grade motor where that punch through due to corona inception voltage actually occurred. Unexpected failures. Here are 14 typical failures that occur in motors. And we are going to cover the ones I've just highlighted very briefly though. So for transient voltages caused by those rapid DVDT transitions, it's best to use a transient voltage surge suppressor. SSI makes these, that's surge suppression instruments. They make them, I've been installing a lot of these lately. Voltage imbalance, it's best to use a power meter and look to see what your balance is on the motor and make sure that you don't exceed 10%. Harmonic distortion, this is one of those hidden ones that affect most everybody and they don't even know it. The 5th, 11th, 17th, 23rd, these odd harmonics are actually negative torque harmonics. They create a negative torque. So if you have the presence of a 5th harmonic, which is pretty high energy in terms of these harmonics, you know, the lower the harmonic value or number, the higher the energy. So a 5th harmonic is actually creating a reverse torque that the primary 60 hertz has to overcome. In one case, we saw a motor that was designed to be loaded 63%. When we actually measured it and saw a significant 5th harmonic, it was loaded 143%, and it was burning out, and they couldn't figure out why when it was only loaded 63%. It was because of the cause of this harmonic. Harmonic distortion, the way it's treated is you use a series trap circuit. You can use different types of detuned trap circuits. The reason why you want it to be detuned is that this literally is a short circuit at the frequency, you know, of the 5th harmonic. So at 300 hertz, which is the 5th harmonic, this would be a dead short and you'd have a very high current, and you don't want that. So you do detune them a little bit. So when you buy these from Siemens, Eaton, or Mirus, these are active switchable harmonic filters that can properly address harmonic issues through their controls to detune the particular harmonics. The reflected waves, so we talked about these rapid DVDT voltages that come off of a VFD motor interaction. You need to be less than 50 feet on that cable. When you get over 50 feet on the cable between the VFD and the motor, you're a prime candidate for resonance in that cable, and reflected waves could very much affect the performance of your installation. Overloading, we see overloading not only just load on the shaft, but because of the 5th harmonic, because of poor temperature management or thermal management. Here you see we used infrared imaging and we saw a plume here at the power connection, which gave us the idea that this was being overloaded. We opened it up, and sure enough, you can see that these wires right here, if I was to show you the actual photograph of the insulation of that wire, it was black due to the char. Shaft voltage, when initially VFDs were used on motors, the high frequency components would transmit through the insulation to the grounded shaft, and that created a current to ground through the rotor. So the solution was grounding rings or a grounded shaft or insulated bearings. All the motor manufacturers today have, you know, mitigating components or solutions for their motors. You just want to make sure that they're specified and that they're stated in the specification. Marathon uses an Aegis shaft grounding, and Balder uses a shaft grounding ring. This is an example of what it looks like when you have sigma current. Here you see a bearing that is running very hot, and it's because of this trace inside the bearing. You see this fluting, and this fluting is an indicator of this sigma voltage or current riding through the bearings, causing an incredible amount of friction. And loose connections. You know, you always want to be aware anytime you open up a panel or a box. First thing we do is use an infrared gun to make sure that we're not dealing with loose connections. And very often we do see loose connections in panels and motors and other types of power connections because they're typically, and I can see in this case, a compression block mounting. And over time, due to the heating and cooling of the wire, you can get thermal expansion, contraction of the copper or the aluminum, and eventually over time that can loosen that connection. So for safety as well as for proper, you know, preventive maintenance and whatnot, you want to make sure that you take precautions to look for loose connections whenever you open up any panel or any power connection box on a motor. In terms of long-term reliability on a motor, the single most important parameters for long-term motor reliability are alignment and footing, how the motor is actually being installed. This is one of the motors that we were going to align on a particular job. So we use vibration analysis and we use alignment tools. Here you see Fluke and Rotoline, two prominent companies with very good tools for alignment. The alignment, there's machine-based and foundation-based. So machine-based, you see a parallel soft foot. So in this case, the mounting platform is flat, but one of the feet is not level with the other feet, and therefore there's this air cushion. This is picked up by the motor as a soft foot. That foot can be bent, and that also creates a soft foot. Here you see the alignment bases are not level and not uniform, and they create these air gaps that will create the soft foot. Soft footing, here you see shims that are used to align the motor, but when you have a bent foot, you create these air gaps and these shims don't fit properly under the foot. And so you get a foot that is what's considered soft. And here you see the offset that creates a soft foot. You never want to stack more than 3 or 4 shims under 1 foot because each shim entraps oxygen or air between them. And when you get enough stacked, it becomes a sponge, and that also creates a soft foot. Shaft alignment, you want to make sure that you're not offset or angular misalignment. I show some tolerances here at 3,600 RPM. You want to be within 1,000th of an inch on angular and offset misalignment. And as you move to lower speeds, you can increase that tolerance up to 3,000ths of an inch. Okay, so that wraps it up. Are there any questions that have come in?
Yeah, there's a lot of questions, Tom. That was really good. I didn't realize how little I knew. Again, that's what I'm learning as I get older. Is I don't know half of what I thought I knew when I was younger. And it's not because I forgot things. It's because I never knew. I just thought I knew. Okay, here's the first one. is motor load essentially load factor? I see 70% used as an assumption.
Yeah, the 70% I used in the equation was just a number. Typically motors, when they're designed for a load, they're typically loaded 70 to 80% to meet the maximum efficiency for that motor. If you go much higher, you're running into heat issues for that motor because of the insulation class. You want to be careful not to exceed the insulation class on the temperature. And as you get lower, of course, you have the power factor issue. So it's good to operate somewhere in that 70 to 80% as a design guideline.
Okay, I've heard the term inverter duty rated is not consistent among manufacturers. If so, how do we navigate knowing when a motor replacement is really necessary to use a VFD? Does a grounding ring mitigate risk of damaging the motor?
No, it actually protects the motor.
Okay,
So
what about the
grounding
first
ring-
part about, yeah, the grounding ring? Yeah, you got that part answered. Okay, let me say, okay, so does that last part was, does a grounding ring mitigate the risk of damaging the motor? You said it protects the motor, so it does mitigate the risk of damaging the motor. Is that correct?
That's correct.
Okay. And then he asked, he said the inverter duty rated is not consistent among manufacturers. So how do we know when a motor replacement is really necessary when, so when people put in VFDs on an existing motor, and it says it's inverter duty, but different manufacturers mean different things by inverter duty. How do you know if it's okay? Does that make sense?
Well, if you look at the motor data label, if it's inverter duty or inverter grade, it'll say right on there.
Right. Well, that's okay. That's what he said. But he said that different manufacturers mean different things when they say inverter duty rated.
Mm-hmm.
I don't know.
Correct.
Just how do you deal with that? I guess is the question.
Right. Yeah. No. Because the inverter grade is a more expensive motor, it's always put on the label and it's specified because it's a premium feature.
Yeah. Yeah. Okay. Does using a VFD to run at lower speeds, does that hurt the motor efficiency on its curve? I actually know the answer to this. This is one I know, but I'm not going to answer it. This is for you to answer.
Yeah, and the motor efficiency improves when you lower the speed, but you want to make sure too, when you do lower the speed, that you don't lower it beyond about 28% or about 25%. Because what happens is, like on a TEFC or a totally enclosed fan, motor, that fan is slowing down and it's not cooling the motor. And that motor is dealing with those harmonics and those issues from the VFD. So it may require, in some cases, a separately controlled fan that operates at full 60 hertz.
Yeah, people don't do that though that often. No, so I read, so I guess maybe what I thought I knew, I don't know. So I read that that at lower VFD speeds, motors actually become less efficient, and that there is, and I actually found these tables online of lower, let's say, how much less efficient a motor is at lower speeds. Have you heard of that?
At the lower speed, it's more efficient with the VFD. So I'm not quite sure what you're referring to.
Yeah. Okay. Well, we'll just leave it at that. I know you know more than I do about motors. I guess I should look into what I was looking at. Yeah. Okay. I sure thought I saw something different. Okay. Is the third harmonic also a negative torque?
No, third harmonic is not a negative torque. No.
Okay. Here's another one. I've never seen the VFD power factor stated at unity. We have a correlation we use to estimate it, usually between 85 to 95% efficiency, depending on the percentage full load amps.
Mm-hmm. Yeah, no, the guideline is about unity. I mean, it's not perfect in every case, but generally, it's about as close to unity as you're going to get in the application. It's the best way to get there or get close.
Okay. Okay. Let's see what this next one is. Okay. I've seen in recent years manufacturers designed smart VFDs, smart VFDs, which can auto detect loads, auto energy optimize loads at best efficiency points in real time, and have conditioning monitoring capabilities. Have you heard about this? Any comments on it?
Yes, for a larger load, that would make sense.
Okay, so you have heard of it. Have you seen it in action?
In one case, yes.
Okay, so you haven't seen many here. Okay. Okay, that's all I got. Oh, I had a question. So I read also that, so this was when an energy engineer is recommending, let's say, changing an air handler from constant volume to VAV, so that means one of the things you're going to do is put a VFD on the motor. And then the question is, do you need to replace, let's say, the existing standard efficiency motor with a premium efficiency, or let's say an inverter duty rated motor? Yes, and you mentioned what we should replace it with a premium, but let's let that go. Just inverter duty rated. And I've heard that there are times when that may not be necessary and the standard efficiency motor can work. One example may be if the cable between the two is like 10 feet or something like 15 feet or less. And I don't remember, there was 2 or 3 other reasons. And if all 3 of these conditions were met, then you probably don't need a inverter duty rated motor. Have you heard of this, or do you believe this?
I do, but it's very conditional, because if the motor is not premium efficient or inverter duty, then it's not designed to handle the heat that will be generated. It's also not designed to handle the voltage spikes that are occurring. The insulation isn't designed for it. And the winding starts and stops at the same point, and that's where you have the maximum voltage spike. So you can compromise the motor very easily with the VFD if it's not inverter rated or premium efficient. The guideline that I've used in the past is to significantly derate the motor. So if it's 100 horsepower and you're going to run it at 50 horsepower or 40 horsepower, you might get along with it. It might be okay if that cable is short and the VFD doesn't have, it's got some IEEE 519 filtering. It's got, the harmonics are reduced because it's an intelligent inverter. If you got all those pieces in place and they're all specified correctly, you can get by derating the motor.
Okay, that's good. That's good. And one other thing, as you said, so you probably should replace the motor as long with it's either an inverter duty rated or a premium efficiency. It doesn't need to be both. Is that correct? One or the other will be good enough.
Right. The premium efficient motor is not necessarily designed to be inverter grade or inverter duty. So it's always best to specify inverter duty or inverter grade. Typically, you'll see inverter duty right on the nameplate, and that's your best because that was designed and built for inverters.
Okay, that's good. That's good. So why is the affinity law coefficient? Why is 2.7 or 2.4 not 3? Is it because of lower overall pump system efficiency?
Right. If the actual efficiency will depend what you attach to that shaft. So is it a gearbox? Is it a gate valve on a motor, on a water pump? Is it an air vane like I showed in my example? What is that load and how efficient can it be, and what efficiency impact will it have on the system. So the power draw off the line through that system may not reflect a 2.7 exponent. It may reflect more of a 2.5 or 4 or 3 exponent because of what's downstream. So you always have to look at the total system, how it's configured, what you're actually driving on that shaft, and what is its impact on the total draw.
Okay. Hey, here's something about that question about the, excuse me, sorry about that. Sorry about my cough in there. So earlier I had a question about the smart VFDs, and someone wrote in response to that, and so then maybe you can comment on it. Someone said, sure, there's a product out there called Cool Blue that is an inductive absorber. They claim to have a better alternative to shaft grounding. Do you have any comments on that?
No, I'd have to see that. That's something I haven't heard of.
Okay, let me see if there's, got a lot of questions. That's good. I think that's it. That's all we got today. Hey, everyone, thanks for coming. This is amazing. We're going to stop exactly on time. Tom, you did a great job. You taught me quite a bit. And I realized, like I said, I didn't know as much as I thought I did. Thank you, everyone. Bye.
Thank you, everybody.